Hello, and welcome to Lecture 1 of the Motion in a Straight Line unit of Phys 1104. While this unit is on motion in a straight line, this lecture is not going to be specific to straight line motion. We're going to look at general ways to represent motion. In the very first lecture in this course, I introduced motion diagrams briefly. And you can draw motion diagrams just thinking conceptually about a motion. You can also generate precise ones from data, such as by video analysis. So we're going to work with motion diagrams quite a bit. And you can tell a lot about the motion of an object directly from its motion diagram. So look at this motion diagram and decide what this object is doing. Be as descriptive as you can. Okay, so you've hopefully come up with some things. I'm sure you can see that it's going left. Now, you might have been tempted, based on things from previous physics courses, to say that it's going in the negative direction. I'm going to say that's wrong. It's definitely going left. Why is it wrong? Well, because we haven't defined our axes. We don't know anything about how to assign numbers to the positions or the velocities yet, and so it's not correct to say it's going in the negative direction. You can also see that it's moving in a straight line. And you can also see that it's speeding up. Now, again, you may have been tempted to say that it's accelerating. Well, yes, it is accelerating, but that's not specific enough, because for a physicist, the word accelerating means changing velocity. Well, there are lots of ways to change velocity. You can speed up, you can slow down, you can change the direction you're going in. So if you just say accelerating, you're not being specific enough. Speeding up is giving more information. Okay, so I'm not going to tell you much about this one until much later. You have a look and decide what this object is doing. Let's say you're texting with your friend Sam. You ask, "Where are you?" And Sam texts back, 12. Well, Sam, that's not a very useful answer. And so you politely say, "Sam, can you tell me a little more?" Well, it might have been more useful for Sam to say something like, "I'm 12 kilometers south of Sydney on Highway 4. And let's pull that apart, because that has all the ingredients of a good position. To usefully specify a position, you need a reference point. So in the case of the sentence above, that's Sydney. You need a direction from the reference point. So for example, south on Highway 4. And you need a distance with units. You'll often find position defined in textbooks as the location of an object, but I don't think that's quite right. I can point at my coffee mug on my desk and say, "It's right there," and I've told you its location, but I don't feel I've given you its position. On the other hand, if I tell you my coffee mug is 1.3 meters from the right edge of my desk and 0.3 meters from the bottom edge of my desk, that is a position. I think that position means a mathematical description of the location of an object, or in other words, position is what you have when you have assigned numbers to a location. A couple of minutes ago in the example with Sam and position, I used Sydney as a reference point for giving a position. Normally what we do is we set axes, and then the origin of our coordinate system is our reference point. Now be careful, many students, when they hear the word origin, they think it means wherever the object whose motion you're describing started. That's not what we mean. Origin is the point where your two axes in your coordinate system cross each other. Here is the supervillain vector showing us some vectors. And the point here is to look at position vectors. And I've drawn position vectors for his squid gun and for the squid that he's just fired from it. And a position vector, as I've shown, always points from the origin to the location of the object, just like these two position vectors. And one thing I want to point out then is that the arrows are the things that are the vectors. You may be able to write down their components, we'll eventually see how to do that, but the arrows themselves are the vectors. And so if you just rotate the axes, the vectors themselves haven't changed. They're still the same arrows. On the other hand, if you translate the axes to a different place, now those vectors have both changed. On the other hand, a displacement vector, a delta x, points from the initial location of an object to the final location, where again, as usual, you have to worry about what you mean by initial and final. So notice again that it doesn't change when you rotate the coordinate system, but this time, because it's from one position to another, from one location to another, and has no connection at all with the location of the origin, when you move the origin, when you move your coordinates, the displacement vector remains unchanged. So given that, I just want to quickly point out that this is a symmetry. Notice that position vectors are invariant under rotation of our coordinates, that's a symmetry, but they are not invariant under translation of the coordinates. On the other hand, displacement vectors are invariant under both rotation and translation of our coordinate system. Now, one thing to note is that we expect our physical laws to be invariant under both rotation and translation. It would be rather strange if our physical law had to be rewritten every time we choose a new coordinate system. And given that, we can expect that we may have physical laws that are expressed in terms of displacement, because those would be invariant, but we don't really expect to find any laws that are expressed in terms of position, because those wouldn't have the right invariance. Let's check your understanding. Some object starts at this x and moves to this x. And I want you to choose which of these shows the correct relationship between the displacement vector and initial and final position vectors for this object.